Hey there, this is a screencast in which I work a related rates example, this one about rising water in a cone. Let me read the problem to you. Water runs into a conical tank at a rate of 9 cubic feet per minute. The cone stands point down and has a height of 10 feet and a base with a radius of 5 feet. How fast is the water rising when the water is 6 feet deep? When you work word problems, there's a couple things that I like to do. One thing I like to do is draw a picture. That gives me a sense of what's happening in the problem. Another thing that it's important to do is to create a bunch of variables. That's an important step in the process of going from a verbal description of a question to a symbolic description of a question. In the symbolic form, we can apply analytic tools of the calculus. Let me draw a picture of what's happening here. We've got a cone, point down. So I'm going to sketch it in perspective here so it looks three-dimensional. You can see what a cone looks like. Water's flowing in at a rate of 9 cubic feet per minute. I'm not going to draw the water, except maybe I'll say, hey, there's some water in the cone. The cone is 10 feet deep and has a base with a radius of 5 feet. So that's this top end here. This is the base, and it has a radius of 5 feet. The question asks, how fast is the water rising when the water is 6 feet deep? So we have this water level, and as water flows in, the water is going up. We want to know how fast is that water level rising. So in the problem, I guess we need to have a variable that describes the height or the depth of the water. So let's do that. I've got my water written into this picture, so say that that's the surface of the water, and there's going to be a depth here. I'm going to call that depth h. So let h be the depth or the height of the water. And let's specify that we're going to measure it in feet, because that's how our cone is measured, and that's related to the unit of the volume of water that goes into the cone. I'm also going to call this distance right here r, the radius of the surface of the water. The problem asks, how fast is the water rising when the water is 6 feet deep? So it's asking, how fast is the water rising when h is 6? We also know how the volume of water is changing. The volume of water is increasing at a rate of 9 cubic feet per minute. So if I let V be the volume of water in the tank, I know that my volume of water is changing at a constant rate of 9 cubic feet per minute. So what I want to do is I want to find a formula that relates volume, for which I have this information, to height, or the depth of the water, because I want to find this information. Looking at the picture over here, the shape of the water is a cone, because the water takes on the shape of the vessel. What's a formula that for the volume of a cone of this shape? And you can look up in a book, and it'll show you that the volume of a cone is 1/3 pi times the square of the radius of the base times the height of the cone. Looking at this, kind of makes us happy. It kind of makes us happy. We have a formula that relates volume on one side and the depth of the water on the other side. But there's an R here. We don't know what R is. However, if you remember from trigonometry, in this picture, we've got two similar triangles. And in similar triangles, you can say the following. You know that in our picture, the ratio of R to H is going to be the same as the ratio of 5 to 10. This red triangle is similar to this green triangle. So the ratio of the measurements of the side length should be the same. From this ratio, we can say 10R equals 5H, or we can simplify that to 2R equals H. In this case, we want to rewrite R in terms of H, so I'm going to write R equals 1/2 H. Substituting this into the volume equation, I get 1/3 pi times the quantity 1/2 H squared times H. And if I multiply that all out, 1/2 squared is a 1/4, so I get 1/12 pi H cubed. That now is an equation that relates my volume to the depth of the water. Looks like we need more space. Volume equals 1/12 pi H cubed. We know dV dt is 9. We want to know what's the depth of the water when the water is 6 feet deep. Let's look at our equation here that relates volume and the depth of the water, and we're going to differentiate both sides using implicit differentiation. On the left-hand side, I get dV dt. On the right-hand side, the constants don't matter. I differentiate my H cubed, and I get 3H squared. Then by the chain rule, I multiply by the derivative of H, and that's our formula. We're interested in understanding how my depth is changing, or at what rate my depth is changing when the depth is 6. We take that H and plug it in, or H equals 6 and plug it in for H. And we get 1/12 pi times 3 times 6 squared dH dt. Meanwhile, we know the volume is 9 cubic feet, or the rate of change of volume is 9 cubic feet per minute. Now we can solve for dH dt. And let's take a couple steps to do this. Multiplying both sides by 12 over pi gives this. And then dividing both sides by 3 times 6 squared gives this. If you work this out, you should get 6 over pi feet per minute. So just a little less than 2. Let's write our final answer in the form of a sentence. When the water is 6 feet deep, the level of the water is increasing at a rate of 6 over pi feet per minute. And that's the answer. Now, I'd like you to try a problem that's very much like this. Water runs into a conical tank at a rate of 10 cubic feet per minute. The cone stands point down and has a height of 12 feet and a base with a radius of 8 feet. How fast is the water rising when the water is halfway to the rim? Use the same approach I did in my example and see if you can come up with an answer. Pause this video at this point and do that work. Come back and I'll show you what I got, and then I'll ask you another question. When I did this problem, I calculated it rises at a rate of about 1.79 feet per minute. Hopefully you got the same thing. Now, something else for you to think about. If the volume of water is flowing into the cone at a constant rate, is the water level in the cone rising at a constant rate? You should have an intuition about this from your lived life. So it's good to think about that for a second. What do you expect to happen? But what I want you to do is use the mathematics to explain what is happening. Explain why the water is doing what you think it should do. If your intuition disagrees with the mathematics, you got to decide which one was right. And hint, the math is right.